In this video, we are going to explain the characteristics of the first derivative of a function. In a similar video in part 1, we saw that the definition of the derivative mt is the limit of the slope of the secant through AB, which is given by fx1 plus delta x minus fx1, divided by delta x as delta x approaches 0. Delta x is now this is x1, and this is the distance between the two, it's delta x, and this is x2, for example. The notation of the first derivative is f dash x1. This is the first derivative at point x1, and the first characteristic is that this value is equal to the slope of the tangent to the curve of the function at point A. So this is characteristic number 1. We also know that the slope indicates the rate of change. So characteristic number 2 is that the derivative, the first derivative at point x1, indicate the rate of change of function f at x equal to x1. We will now look at some special point at which the first derivative is equal to 0, and therefore the slope of the tangent is also equal to 0, which gives a tangent that is parallel to the x-axis. Now we start with the small video changing the position of A. Now A is close to the maximum point. Now there is one specific value of the position of A along the x-axis that will give d equal to 0. This is being calculated, and here we are, d equal to 0. Now we go to the next minimum point. The same thing, d is slightly positive, negative as you go close to this point, but there is a specific value of A that gives d equal to 0, and the tangent is parallel to the x-axis, indicating that the slope is 0. Another maximum, and again the value of the x for which d equal to 0 is being calculated, and here also there is a specific value that gives d equal to 0. So the third characteristic of the first derivative is that the derivative is equal to 0 at the local maxima and minima of the function. They are also called stationary points, let's underline all this: maxima, minima, stationary point, and they are also called critical points. We will now look at the relationship between the increase and decrease of a function and the sign of the derivative, or the sign of the slope of the tangent to the curve. Now let's start the video on the right, and on the first interval we see that the slope is positive due to the fact that the function itself is increasing on this interval. Now we continue to the next interval from the maximum to the minimum point, and we will see that the tangent has a slope that is negative. Therefore, the derivative is negative when the function is decreasing. Next, the function is increasing, the derivative is positive, and then the function is decreasing and the derivative d, or the slope, is negative, and so on. We can now write characteristic number 4, which is if the function increases over any interval for which the first derivative is positive, f decreases over any interval for which the first derivative fx prime is less than 0. We will now examine the value, the absolute value of the derivative and the rate at which the function changes. Now we will start our video with the first interval. We know that here the derivative is 3.77 on average. Then we continue. Here it's about negative 11, or the absolute value is 11. Now we go to the next. Here it's about 20, close to 24. Then as we continue, where the function varies rapidly now, the absolute value of the derivative increases, almost 30 here. Here it's around 50, and then here it's around 60 something, and here around 72. So characteristic number 5, we will say that the absolute value of the derivative increases as the function increases or decreases rapidly. We will now look at the relationship between the graph of the tangent in red and the graph of the function. Now remember that the slope of the tangent is equal to the first derivative. In fact, we are looking at a relationship between the function and its first derivative. So let's start the video here. Now we start with the first point. Now we are zooming in at that point, and we can see that around point A, for points close to A, the two graphs are almost the same. Now let's continue. That's a point close to the maximum. Again, when we zoom in, we can see that the two graphs are very close. Now let's continue. So around A, they're very close. Now we continue to another point. We zoom in, and again the graph in blue, that of the function, and the tangent line are very close. This is characteristic number 6. And we are going to say that the equation of the tangent line may be used to approximate the function around the point of tangency, point A in our case. This is a very important characteristic of the first derivative in calculus.